Next thing I'd like to show you is, again, we're on the neck-off slice. I want to show you the structure of the velocity. Here I've changed the vectors in contrast to the previous video when the vectors were surface vectors. These are the velocity vectors of the vertically average velocity. So imagine that the velocity at the bottom and the surface are in general different, and if we average from the bottom to the surface we get the vertical average. So if the surface going the opposite direction of the bottom with the same magnitude, the average will be 0. They cancel each other out. So these are the vertically average vectors, so it represents a little bit more thinking about the mass transport of the water from a two-dimensional point of view. It's easier to think about. So these vectors again are different, scales are the same, and color rendering is as it is prior, is the vertically average velocity magnitude. So where it's high here, the vector should be long as well. Up here is a slice, so you see a black line through the bay. That's a transect across the bay, roughly the path of the boat cruise. Not quite, we didn't go on a very straight line. So across the bay over to Nashan here, and then starting from Sconnecut Neck here. And this shows the velocity across that transect. So I project the velocity. What this is a measure of is the strength of the currents going across the line. If the local velocity was parallel to the line, it would show up as 0 here. So this is the velocity component normal to that, or orthogonal to that line. The left side of this is the west side of the bay, the shallow part of the bay. The east side of this is Nashan. Again, so the depth deeper part of the bay is towards the east. Let me start it from 0. Where's my time slider? 1 second. There it is. Okay, let's put that over here. So start here, and you'll notice in here, so the contours, the dash contours are ISO velocity lines, constant magnitude velocity. They're not labeled, but you get a sense of stronger and weaker. Now the dash lines are negative velocities, and negative in this sense is up bay towards the Cape Cod Canal. Positive in our diagram is down bay, heading towards the southwest, heading away from the Cape Cod Canal. Positive contours are solid lines. The very thick line is a 0 contour. It's a line dividing water moving up bay, dash lines, and water moving down bay, solid lines. So the thick solid line is a zero velocity. At that point, the water is not moving normal to the plane, normal to the transect. So let's go through the day, go through our day. And again, the water surface here's flood tide at 5 a.m. Remember we saw the peak surface currents right around in between flood tide and ebb tide in our standing wave system. Let's see if we can just FF to there, and watch what's happening. So the right here we're mostly flooding. We're mostly flooding into the bay. Most of the bay water here across this transect is dash line, meaning it's moving up bay. Some water is actually moving down way. So there's a shear at the surface, up bay, down bay. And this is in the real-time frame. This is not subtidal. So that shows you the strength of the wind. It's basically pushing the water at the surface against the general flow of the bay, at least in the model. So who knows if that's real or not, but that can happen. So now we will move towards peak high tide, and there we are. At some point here we should be in between low tide and high tide. We should be reaching a point where we have peak flood. So I did see a snapshot where we had all the bay water moving up. So there is a moment where all the bay water is moving, and the transect is moving up bay. Strongest or most negative down here in the deep water, weakest at the surface where the wind is trying its best to keep this from happening at all. So the wind's not winning at this point, but it's doing its job to bring as close to 0 as possible, say maybe 2 centimeters per second, versus in the deep waters close to 30. So still significant shear, but it is unidirectional. as we approach high tide, and now we're turning around towards peak ebb. So now both the tide and the wind are working together, and you can see here we're starting to see red and solid contours come in. There's one bolus of the bay that's still moving up bay, and that should erase. So at some point here, the whole bay is moving out. The water's all moving out at this point. Peak velocities at the surface again, because the wind is working with the tidal pressure gradient, weaker near the bottom, but everything is positive. And then this will essentially repeat itself. This is probably the point of peak ebb. Then things start to turn around. Now we're starting to see some up bay water at depth. And so again, we have wind stress acting on the surface out of the screen, and the pressure gradients turn around in the sense that the tide wave is trying to push up the bay. And so pressure gradients reach to depth, so it's affecting this water parcel here, knows nothing about the wind essentially, and is getting the sense of the tide. This water parcel up here is feeling both the tide and the wind is still winning. And then eventually the tide gets stronger against the wind. I'm sorry about that, that's a rendering problem. And then we get to the point where most of the bay again is going up bay with the tide, just the surface water is coming down bay, and then at that point, actually we didn't see a complete up bay motion on this round as we did over here around 2 a.m. and that's because the wind strengthened during the day. So it was some northeast wind in the morning, and it was strongest actually when we were on the water going out. So these results are quite difficult to achieve in the model. In fact, this model that I'm working with here, and I'll show you the vertical grid, it has, due to basically limits of CPU time, I apologize, give me 1 second. Okay, there's the grid. So you can see the layers here. It's stacks of triangles on top of each other, and each of these blocks here and each of these blocks here, there's a triangle stacked up on top of each other. It makes a prisms, a stack of prisms going up. And each of those are solving these conservation equations. And these are difficult things to deal with. In this case, you have a strong shear, and the shear will induce strong mixing. And if you don't have the resolution around the mixing line, then you can poorly resolve the mixing. And so how the wind stress influences deep water, how deep water motion is tugging on the surface water, depends very strongly on this mixing. So it's an important thing to look at and resolve. Let me get rid of that. I think that's all I wanted to say about this. So we'll keep this in mind. It's important that there is some two-way flow, but there is definitely unidirectional flow as well. When you get to peak flood, and in particular peak ebb, the flow is most definitely coming completely out of the bay or completely into the bay. But at the crossover times, because as the tide weakens and goes to zero as it switches over, the wind's still cranking, so then you have a stronger shear because it's continuing pulling the surface. The winds weren't strong, but they were strong enough to have an effect on that day. And we looked at the winds in a prior video.